So in last lecture, we studied Maxwell equation in integral and differential form. The topic of today's lecture is Maxwell equation in phasor form. So this is a continuation of previous lecture. The relevant section in your book are section 9.5 and section 9.7. The topic covered in today's lecture are: first we learn what is meant by time harmonic quantities. Then we understand the difference between scalar phasor and vector phasor. And then we express the Maxwell equation in phasor form. And lastly, we will learn how to find electric field given the magnetic field, or vice versa, that is given the magnetic field, how to find the electric field with the help of phasor form of Maxwell equation. So let's first study what is meant by time harmonic quantities. The quantities that vary sinusoidally with time are called the time harmonic quantities. So sinusoidal quantities mathematically can be written as a function of sine or cosine, but we will use cosine as our reference. And if we have a sine signal, we will express in terms of cosine, as we did in the network analysis course. So this is a typical expression for a sinusoidal varying or time harmonic voltage signal. So here A is amplitude, omega is the angular frequency, and phi is the phase in radian. So we express a instantaneous signal in time domain which varies sinusoidally using this type of expression, that is A cosine omega t plus phi. The frequency in hertz is related to this angular frequency using this expression, that is omega is equal to 2 pi f, and the time period and frequency are inversely related. Now using the Euler identity. So this is the Euler identity, that is exponential of j omega t plus phi is equal to cosine omega t plus phi plus j sine omega t plus phi. We can express this quantity, instantaneous time domain quantity, in phasor form. So for example, if I multiply this expression, this Euler identity, with A on both sides, let's say if I multiply A on left hand side and on right hand side, we have A and then we have A here. So this part here is actually real part of, this is the real part, and this is A sine omega t plus phi part is the imaginary part of this complex quantity. Now another way of writing this is that this is real part of this quantity. So I can write this as real part of A exponential of j omega t plus phi. This left hand side is basically A cosine omega t plus phi. So this was the real part of this quantity, so we write it like this. So when we write it like this, then I can also write it like A exponential of j phi and exponential of j omega t. So when we write this instantaneous quantity, obviously this is equal to this instantaneous quantity. So when we write the instantaneous time domain signal in this form, then by definition, this quantity here is called the phasor. It is a complex number used to represent the magnitude and phase of a time domain or instantaneous quantity. So this is the basic fundamental definition of phasor. So using Euler identity, we can write this thing as real part of A exponential of j phi exponential j omega t. And as I said earlier, that when we write it in this form, then this quantity, this complex quantity, which represent the magnitude and phase of the time domain signal is called the phasor. So this is by definition the definition of phasor. When you express it like this, then if you leave this real and exponent j omega t part, then this quantity is the phasor, and we denote it by capital letter V, and this subscript S is denoting that we are talking about the sinusoidal varying quantity. So this is this A exponential j phi is by definition this phasor Vs. So we can also write it that this phasor when multiplied by exponential of j omega t, and if we take the real part, then we get this time domain signal back. So here are the summary. If we have a instantaneous time domain signal v of t a cosine omega t plus phi, if this is the time domain signal, and if we want to convert it into phasor domain, time domain to phasor domain, this is phasor domain is also called the frequency domain. Then we can take this magnitude and phase and of the instantaneous signal and represent it as a complex number, which is also called the phasor. So this is the phasor form of this complex this instantaneous signal. On the other hand, if we are given this phasor form, so this was the phasor form. Now, if we are given this phasor form and you are asked to convert back into instantaneous form, then you can use this fundamental definition. You multiply this phasor V of S and by this exponential of j omega t and take the real part. In this way, you can convert from phasor domain back into time domain. So note the notation here that small letter v with this function symbol t, v of t is representing the time domain signal, and this capital letter V with subscript S is representing the phasor domain signal. Let's take an example. So we are given a voltage signal V of t a sine omega t plus phi. We want to convert this time harmonic or instantaneous signal into phasor form. So what should we do? Can I write it like this? That is V S, let's say phasor corresponding to this is a exponential of j phi. Is it right or wrong?
Right, sir.
ठीक है. Any other person? कोई और बंदा आंसर देना चाह रहा है इसको? इनका ख्याल तो ये है कि ये ठीक है जो. Actually, you are missing one thing, that this is a sine omega t plus phi. So our fundamental definition of phasor was that if we have a time domain signal a cosine omega t plus phi, then we can write it in phasor form v of s is equal to a exponential of j phi. But here we don't have this cosine signal. It is a sine signal. So first step should be that we have to convert this sine signal back into cosine signal. We cannot write this, so this is actually wrong. So the first step should be that we should write this signal in the form of cosine. So what we can do is that v of t is equal to a cosine omega t plus phi minus pi by 2, because we have a trigonometric identity that is sine alpha is equal to cosine alpha minus 90 degree. Or you can think it as graphically let's say if we have a cosine graph, let's say this is my cosine alpha, let's say, as a function of time. Now, if I ask you that what will be the graph of cosine alpha minus 90, cosine alpha minus, let's say, pi by 2. What should be the graph? It will, this original graph will shift left or right. If cosine alpha graph is this, then what will be the graph of cosine alpha minus pi by 2?
So right shift.
It should be shifted on the right side, because then the function argument, if we make the function argument 0, that is alpha minus pi by 2 equal to 0, it should be occur at alpha is equal to plus pi by 2. So this is alpha is equal to, so this should be not, this should be pi by 2, let's say. So this whole graph will be shifted rightward. So if I extrapolate this graph, what this function look like? This is actually sine alpha. So this means that cosine alpha minus pi by 2 is sine alpha. This was the trigonometric identity we are using. So the first step was to convert this sine omega t plus phi in terms of cosine. So all we have to do is subtract minus pi by 2 from the argument of this cosine signal. Then the whole graph will be shifted right and it will become the sine signal. Now we can write the phasor form. Now the phasor is V of S is the, we have to take the amplitude, which is A, and the phase. The phase in this case is this whole thing, this omega. The term beside this omega t, we have two terms, phi and minus pi by 2. So I can write this as exponential of j pi minus pi by 2. This is the phasor form. So I can actually simplify this further. I can also write it as A you can also if you want, you can also express it in the fundamental definition form. For example, you can write this form V of t like this. If you want, real part of exponential j omega t, then you can recognize that this part beside this real and exponential j omega t is the phasor form by definition. So this is the phasor, or you can write it directly. So whichever method suits you, you can use. So Vs is the phasor, which is this part, A exponential of j phi and exponential of minus j pi by 2. What is this exponential of minus j pi by 2? What is this term is equal to?
So shift.
I told you in last lecture that you can think it as a unity circle, and let's say
Minus j, sir.
Yes, this is the correct answer. So this is the phi. So at phi is equal to minus pi by 2, this is, let's say, real axis and this is the imaginary axis. Then we will be at this point, which is minus j. So this should be, this can be written as A exponential of j phi, and this whole term will become minus j. So this is the final form of this phasor. Minus j A exponential of j pi. Our next, let's move back. So this was the phasor. This was the scalar phasor. What we were talking about, this thing was the scalar phasor. We don't have a unit vector, ax unit vector, ay unit vector, or az unit vector. It's just a complex number. So it is a scalar phasor. So let's now talk about the vector phasor, because the field in electric field and magnetic field are spatio-temporal in nature, and they are also a vector quantity. So this is the general expression of the electric field. It's a vector, instantaneous vector field. So it's a vector. This means that it should have three components, x component, y component, and z component. And it is also a function. It is a function of space coordinate x, y, z, as well as the time coordinate t. So it's a spatio-temporal signal. On the other, so this is the instantaneous vector field, and this thing here, in which we are denoted as ES with the vector sign x, y, z. This is the phasor vector. Phasor vector. It's a phasor. It's a complex number. It does not have time dependence. And at the same time, it's a vector. It will have x, y, and z component. So these two are related. This instantaneous vector field and phasor vector field, they are related by this fundamental definition, that if we take the phasor, multiply it with the exponential of j omega t, and take the real part, we get the time domain signal. This is the similar definition we are using for the case of scalar phasor. But you have to carefully differentiate between the scalar phasor as well as the vector phasor. Vector phasor has this bar sign, which means it has the three components. On the other hand, scalar phasor had only single value. It does not have any direction. Okay. So as I was talking, that this time domain signal can have three components: x component, y component, and z component. So we are denoting this whole thing exponential of the electric field as a function of x, y, z, and time by a shorthand notation. That is, we are denoting it by simple E. So if I denote it by E and denote this whole thing as by shorthand notation ES, then I can write this time domain instantaneous vector field as sum of three components. That is, x component along ax unit vector, y component along ay unit vector, and z component along az unit vector. Because this vector, it must have three components in general. So now if we are talking about the timed harmonic quantity. So if we assume that they are time harmonic or sinusoidal variations, then we can write this thing. Now please note that E and E, X, Y, Z, and T are one and same thing. This is just the shorthand notations. So for sinusoidal case, we can write this EX as AX cosine omega t plus phi. So AX is the magnitude and phi x is the phase, and this is, so EX is varying sinusoidally. Similarly, EY can also be written as AY cosine omega t plus phi. So AY is again amplitude and phi is the phase. Similarly, this scalar component EZ can also be written using sinusoidal assumption that it has magnitude AZ and phase phi z. Please note that I have simplified the notation. In general, this AX will also be a function of x, y, z, and t. And this phi x will also be a function of x, y, z, and t. So both amplitude and phase of a sinusoid can also be are spatio-temporal in nature. It's not. It is not necessary that it's just a constant. Okay. So this was the time domain signal instantaneous vector field. So this is our instantaneous vector field. Now we want to write this into the phasor domain. So we want to have a vector phasor corresponding to this vector field, instantaneous field. So what we can do is that we can use this fundamental definition of the phasor. So this, we pick the amplitude ax and phase phi x, and we can write this as ax exponential of j phi. And because it's a vector, so we also have to take into account this ax unit vector. Similarly, for this second component, we pick the amplitude ay and phase phi and write it as a phasor ay exponential of j phi y. And because it's a vector, we are also writing this ay. Similarly, for third component, we are picking this amplitude az and phase phi z and writing it as a scalar vector az exponential of j phi z. And because it's a vector, we have to write this az. So this whole thing is this three component whole thing is a phasor vector. So this is a phasor vector. And obviously it has three component. So this exs is same thing as ax exponential of j phi x. Eys, the scalar component, is denoted by ay exponential of j phi, and ezs is denoting this component. So to summarize, we have a instantaneous vector field which have three components, and corresponding to that we have a vector phasor which is related to this time domain signal using this fundamental definition. And obviously this phasor vector also has three components like the instantaneous time domain signal, but in the phasor domain, the time domain variation will be suppressed. And please also take into account the notation. We are using exponential electric field with a vector sign and x, y, z, comma t. So this is my instantaneous vector field. On the other hand, when we suppress this time variation and use this subscript s, then we are denoting the phasor vector corresponding to this instantaneous vector field. We can also use a shorthand notation. Instead of writing this whole thing, we can just write this e. So this e is same thing as this whole thing. Similarly, we can also write, instead of this whole thing, this es with vector sign. So this is your book notation. I will also use this alternate definition shorthand notation for these two quantities, in which I will express this thing with a function argument t and this phasor with simple electric field E. I will drop this subscript s. So it is sometimes convenient when we will be working for the phasor. It is inconvenient to write this subscript s again and again. So I will use this alternate shorthand notation. So I will denote the time domain signal like this and the phasor domain signal like this. So these two are the shorthand notation for these two instantaneous and phasor vectors. Let's do an example. So we are given a phasor vector. Please note that now we have only one vector component. In general, how many components we can have? कितने component हो सकते हैं in general? Three components. So here we have only this single x component. We want to find the instantaneous form corresponding to this phasor vector. So what should we do? क्या करना चाहिए? How can we find this instantaneous form? What we can do is that we take this phasor Bs, phasor vector, and multiply it with exponential of j omega t and take the real part. Basically, we are using the fundamental definition of the phasor. Then we can get the time domain signal back. So I am using this alternate notation now. Okay, so Bs, let's put the value of Bs in this expression. We have real Bs was 20 by j ax unit vector exponential of j omega t. In next step, we can write this as minus j 20 ax exponential of j omega t. Next, we can write this minus j, as 20 ax unit vector. This minus j can be written as exponential of what? अभी थोड़ी देर पहले किया था ये जो exponential of what? Minus j can be exponential of pi by 2 or minus j pi?
It is minus j.
Minus j pi by 2. Exponential of j omega t. Or we can write, instead of this, let's do it in another way. We can do it more simplified way by using, let's say, what we can do is that if I expand this exponential of j omega t using Euler identity, I can write this thing as cosine omega t plus j sine omega t. This was the Euler identity. I'm using the Euler identity to expand this. Now, can anybody tell me that what is the real part of this thing? This minus j20x will be multiplied by this cosine omega t as well as this j sine omega t. Then what will be the real part of this expression?
Sir, cos
sine omega t.
सर साइन वाली आ जाएगी सर साइन ओमेगा टी के
20
साथ
sin omega t.
Yes,
j square हो
this
जाएगा वो।
expression, because yes, j and j will become j square, and j square is -1, and minus, we have a minus sign already, so it will become plus. So we have 20 sine omega t, or obviously it's a vector. This ax unit vector will remain as it is. So this is the instantaneous time domain signal corresponding to time domain vector signal corresponding to this phasor form. Okay, this is another example. We are given a phasor. Now we have two components, x component as well as y component. In general, we can have three components. And we want to convert back into time domain. So again, we can use the same trick that we use the fundamental definition of phasor. We multiply this phasor with exponential of j omega t and take the real part. And this will give us the corresponding time domain vector. Okay, let's put the value of as in this expression. We have ax unit vector plus j ay unit vector, and let's expand this exponential j omega t using the Euler identity. We have cosine omega t plus j sine omega t. Now can anybody tell me what will be the real part of this thing? So this AX unit vector will be multiplied by all this thing, and JAY will also be multiplied by these two terms. So for, let's say, for first term, AX unit vector, when multiplied by this thing, what is the real part of this AX when AX will be multiplied by these?
Cos
So
omega
we
t,
have
sir.
AX unit vector cosine omega t. Please don't forget this AX unit vector too, because we are talking about vector phases now. Now, when this second term JAY unit vector will be multiplied by these two terms, what will be the real part of this?
Sin omega t, sir. We can minus
minus
sin.
minus sine omega t and AY unit vector. So this is the corresponding time domain signal corresponding to this vector phasor. So here's a concept question. We are given a time harmonic or instantaneous magnetic field. It is 2 cosine 2x 10 raised to power 10 to the power 8t minus 3y az unit vector. So what's this thing, by the way? 2 into 10 to the power 8.
Omega, sir.
So this is the omega. So we want to convert this instantaneous signal into phasor form. How can we do this? We can write this instantaneous time domain signal h of t using fundamental definition real in phasor. When we write the phasor, we simply pick the magnitude and the phase and write it as a complex number. So I am picking the magnitude 2 and the phase here is minus 3y. So I will write j or minus 3y. So this is the complex number corresponding to this time domain signal. And because it's a vector, I must also write this az unit vector. And this exponential of j omega t, if I take, this is the fundamental definition. So I can also write this simply by expansion. So this term beside this exponential j omega t and real part is basically the phasor. So you can write it like this, or you can write it directly. You can simply also write it like this, that it is the phasor is, sorry. For phasor, we are using this H, capital H, without this time dependence. So I can simply write the phasor, that is 2 exponential of minus j 3y az unit vector, which is basically from fundamental definition. So this is the phasor vector corresponding to this time domains instantaneous vector signal.
सर ये दोबारा बता दें.
Simply, when you write the scalar phasor, let's say v of t is equal to, let's say, 2 cosine, let's say, omega t plus, let's say, 10 degree. And if I ask you to write the phasor corresponding to this, you have done in network analysis in lot of time. So you simply do is that let's say we denote the phasor with capital letter V. So you pick this magnitude 2 and pick this phase and write it as a complex number. So we are doing same thing. We are picking this magnitude 2 and we are picking this phase minus 3y and writing it as a complex number, just like this. The only difference is that now this was a scalar phasor. It has no unit vector. Now we have a vector phasor. There will be a unit vector. And in general, it can also have other component. For example, a second component or plus a third component. On the other hand, in scalar phasor, we only have a single number. So this is the difference. all the concept you are using in the circuit theory are also applicable. Only difference is that this is the unit vector is also written, and we have three. We can in general now have three components. Okay, next we want to convert the Maxwell equation into phasor or frequency domain. So we are again assuming the time harmonic or exponential j omega t variations of signal. So this was the Maxwell equation in point or differential form. So can anybody tell me that differentiation in time domain is equivalent to what? So what will be partial over partial t in time domain is equivalent to in frequency domain? What will be this become? We are assuming this time harmonic or exponential j omega t variation.
2 pi f.
Differentiation in time domain is equal to multiplication in the phasor domain.
सर वो मल्टीप्लाई होता है ना. सही है.
So what will be
j omega.
Simple j omega, because if you differentiate this exponential of j omega t, you will get j omega time exponential of j omega t. So this differentiation is equivalent to multiplication by j omega in the phasor domain. You are using this fact for impedance. For example, if I write this I is equal to c dv by dt, then I can write it in the phasor domain IC. We replace this d by dt by j omega and this v. So I can write this as v by I, which was the impedance concept in the AC impedance. So it become 1 by j omega c. So this was the concept you are using again and again. So the point is that the differentiation in time domain is equivalent to multiplication by j omega. So if you want to convert this Maxwell equation back into the phasor domain, all you have to do is to replace this partial or partial t term with this j omega. And obviously we are also using this subscript s to denote that it is phasor. So in this case, again, I replace this partial or partial t term with j omega. All other term remain same. So in this way, by replacing partial or partial t with j omega, you can simply write the Maxwell equation in the phasor form. Or in alternate notation, which I will use, I'm denoting the time domain signal with this signal, exponent electric field with this time dependence. So this is the time domain differential form, and the phasor form, I am dropping this s subscript and simply writing it e. So this, and other thing is same, that partial of partial t is replaced by j omega. Again, partial of partial t is replaced by j omega. So this is a kind of simplified notation, which I will be using for the phasor. In this, the key difference is that I am not using this subscript s, which is annoying when doing the problem solving. So the last thing we want to do in this lecture is to express if we are given electric field, let's say, how to find the magnetic field using Maxwell equation. And let's say we are given the electric field and we want to find the magnetic field. How can we do this using Maxwell equation? So first, let's say we are given the time domain signal, and this is also our time domain signal. So this is the given, and this is what we want to find. So what we do this in 3 steps. First step is to express this time domain electric field in phasor form. Then we use the phasor form of Maxwell equation to find the corresponding magnetic field. And the third step is that in this step we will find the magnetic field in phasor form. And the last step will be to convert this magnetic field, this phasor magnetic field, back into instantaneous or time domain form. Obviously, if we are given magnetic field, we can also convert it back to electric field using the same steps. So I want to elaborate on this step, that is how to use Maxwell equation to find H field, let's say given E field, and how to find the E field, let's say we are given the H field. So for these steps, what we can use is Maxwell curl equation. So we have two curl equations. Let's say curl of E is minus rate of change of B. So minus J omega mu H. So this is the Faraday's law. And the second curl equation is curl of H is rate of change of D, J omega epsilon E. So this is basically the Ampere's law for source free region. We are assuming that J is equal to 0 or source free region. So these two are equations which will be used to find the magnetic electric field given the, for example, this first equation will be used to find the magnetic field given the electric field. If we are given the electric field and we want to find the magnetic field, we can use this equation. On the other hand, if we are given the magnetic field and we want to find the electric field, then we can use this second equation. So let's apply it on an example. So we are given the magnetic field, let's say time domain magnetic field, and we want to find the corresponding time domain electric field. So let's apply these steps. So first step was to convert this time domain signal into phasor form. So I can write this H in phasor form. I have to pick this magnitude 2 and this phase 2 exponential of minus j 3y, and obviously it's a vector, so we must write this as a unit. So this is the phasor vector corresponding to this time domain vector signal. So this was our first step. Next, we have to use the Maxwell equation phasor form to convert this H to find the electric field. So which equation should I use? First was the curl of E is equal to, let's say we are given curl of H. So we should use curl of H equation. So curl of H is equal to rate of change of D, J omega epsilon E. So this is our equation. There's one thing missing. The medium is sigma is 0. This mu is 2 mu naught, and epsilon is 5 epsilon naught. So this is given. This is given in the problem. So this medium is given. So first we convert this into phasor form. Now we are using the Maxwell curl equation to find this electric field. So
सर इसको h of s लिख दिया करें.
क्या लिख दें?
अरे h of s लिख दिया करें इसको, फिर नहीं तो बंदा कंफ्यूज हो जाता है.
So I am using this expression. For time domain, I am using this subscript t, and for phasor domain, I am using without this t. So this is alternate notation. ये मैं use करूँगा. Okay, so for the electric field, this is phasor vector. I will write it 1 by j omega epsilon and curl of H. And curl of H is equal to, let's say I come here, then I can also write it as E is equal to 1 by j omega epsilon. So curl of H can be written as a x unit vector, a y unit vector, a z unit vector, and partial of partial x, partial of partial y, partial of partial z, hx, hy, and hz. So this is the fundamental definition of curl of a vector in Cartesian coordinate. So I expanded this curl of H. Now, which component do I have? Hx component, hy, and hz component. कौन से component है in phasor form? This was our phasor vector. We only have which component? X, y, or z component.
Z component, sir.
We have only Z components. This is HZAZ. So this means that these two components are actually 0. What about the function dependent? This H is a function of X, Y, or Z. So this HZ is a function of what?
Sir, Z. What?
This is a function of Y, this thing. This AZ unit vector is just telling that it's a vector. So this, if I ask you with what vector होना एक और बात है, और जो है उसका फिर यानी function होना different चीज है. Function mean that it is varying with this quantity. So this is a function of only Y. So this means that this derivative term, X derivative and Z derivative will also be 0. So now if I put my values, let's say 1 by j omega epsilon ax unit vector, ay unit vector, az unit vector, 0 0, sorry, this was partial or partial y 0, and this was 0, this was 0, and this was hz. Now I can expand this 1 by j omega epsilon. So ax will be, if we expand this, we have ax unit vector and partial of partial y of hz. And all other term will be 0. So ay times this 0 times 0 plus az is also this, all other term are 0. You can check this. So hz is given. Hz was this 2 exponential of minus 3y. So I can substitute this 1 by j omega epsilon ax unit vector partial and partial y of hz. Hz is 2 exponential of minus 3y minus j3y. Now, if I take the derivative, I can write this as 1 by j omega epsilon ax unit vector. And what will be the derivative of this? This will become minus 6 exponential minus 6j exponential of minus j3y. So this j will be cancelled, and we will get this. Now if we know the value of omega and epsilon, omega is this thing, this is omega 2 into 10 power 8, and epsilon is given in the problem that epsilon is 5 epsilon naught. So if I substitute the value of omega and epsilon here, and after a few steps you will get minus 678 exponential of minus j3y ax unit vector. So this is my electric field in the phasor domain. Now if we the last step is to convert back into instantaneous form. So to convert back into instantaneous form, what you have to do is that take this vector phasor, multiply it with exponential of j omega t, and take the real part. So the final answer is that electric field will become minus 678 cosine omega was 2 into 10 power 8t minus 3y ax unit vector. So this is our final electric field, time domain electric field in the instantaneous form. So this is an important concept that you should be able to use the Maxwell equation to convert. Let's say you are given the magnetic field, you should be able to find the corresponding electric field using Maxwell equation. Similarly, if you are given the, let's say, electric field, you should be able to find the corresponding magnetic field. So as a homework, you should try this problem. You have to use the Maxwell equation. You are given this electric field, you have to find the corresponding time domain magnetic field using the Maxwell equation. Again, you have to follow the same step as we have done in this example. So with this, we come to end of this lecture.